Welcome to Lab 9, where we will be speaking a little bit about correlation and simple linear regression. Right, so what's a correlation? Basically, we use a correlation to assess the linear relationship between two continuous variables. In our last lesson, we looked at when we're comparing two um, variables that have categories, right? Proportional variables. Well, now we're going to speak a little bit about when we're comparing two variables that are both continuous numerical variables. Right? So we call the variable our independent variable, right? Our variable that we're assuming to be our predictor, we call that variable x. And we want to plot that along the x-axis, right? Then we have our outcome variable, our dependent variable, that's known as y. And really quickly, the statistic that we're going to be looking at in this section, in this topic, is known as our R statistic. And really quickly, I just want to show you a little bit the demonstration of a correlation using a hypothetical example. So let's say we have, this is known as our x-axis, right? Axis. And then we know that this is going to be called the y-axis, right? What we're doing here is we're basically going to be using, graphical representations sort of similar to these to come up with a statistic known as our R. Okay, so let's say we want to look at the relationship that your age, right, in years has on years has on, let's say we want to know whether age has an effect on your weight, right? So this will be considered our x, right? Our independent variable, right? Independent. You get the rest. Independent variable. And weight will be known as our outcome variable or our y, right? And we also say that that's our dependent variable, right? Our dependent variable is dependent upon whatever's going on with our x, right? Our independent variable. Oh, my screen's gonna cut off. Here we are. So what I want to show you is, let's say I put some hypothetical ages here. Let me bring that up real quick. Let's say I have some hypothetical ages. Okay, so we have these weights here. Let me make this bigger so you guys can see. And what we want to do is we would like to say, okay, let's say we have a person in our data that's 20 years old, right? This is 20. And they weigh about 130 pounds or something like that. And then we have another person in our data set that's 30 years old and they weigh, say, maybe about 145. And then we have a person in our data set that's 40 years old and weighs about 150, for example. Then we have, 150. It's like about right here. Then we have someone who's 50 and they maybe just weigh just about 153 pounds. Sorry, trying to plot this right. 153. And the person that's 60 years old, say they weigh about 170, right? So when we're doing a correlation, we're basically looking to see whether or not there's a relationship. And in this case, if I wanted to draw a best fit line through these data points, I would get a straight linear line, right? So what we know about this relationship, we would consider this a positive relationship, right? And because it's linear, this would be known as a strong correlation. And when you have a strong correlation like this, in this case, your R statistic, and as you guys learned from the lecture, R, right, is a value anywhere between -1 and +1. So when you're having a positive relationship like this, you have a R value that would be equal to 1. And when we look at like actual results and actual data, sometimes it's not exactly 1, it'll be like 0.95 or like point, 9, 1, etc., etc. But this is still indicating a very strong correlation. It's very close to 1. If you rounded, this up 0.95 or 0.91 up, you'll get a strong correlation there. So this would be an example of what would be something we'd be looking at and something we'd be comparing. And it'll tell us an assessment of the strength of our relationship. Say, for example, who knows? I mean, this is not the truth, but that would tell us basically, wait, actually, let me put this back. This would say, okay, this strong relationship is showing us that the older you are, the more potentially weight you will have, on your body when you weigh yourself. Say, what if it was actually the other way around? What if the person who was 20-year-old who was 180 pounds, the person who was 30 was 160 pounds, the person who's 40 years old was 150, the person who was 50 was 140, and say the person who was 60 years old is actually like weaker. This is just an example, and I'm sure if you test this in different populations, you'll get different results depending on what you're looking at. Maybe you want to test this in young people, or, well, not even necessarily young people because we're going up to age 60, but maybe you want to test this in people who have, I don't know, some kind of disease that you're interested in. You may actually find a relationship like this where, you know, the younger you are, the more weight you may actually have. I'm not really sure of what population this could be, but this is just a hypothetical sample, right? In this case, your R value would be, can anyone guess? Your R value would be, when it's linear relationship, like the perfect linear relationship like this, your R value would be equal to -1. Okay, so this is more what we're going to also be looking at throughout this lesson and this lab. And then I just kind of want to show you one more thing. Let me do a new page. One more thing. When you have a R, so as we saw, this perfect linear relationship, right? Sort of like what we noticed there. We have these dots in a linear fashion. We know that our R value is going to be equal to 1. And that when we have a relationship that looks like this, these are all scatter plots, right, by the way, then we will know that our R is going to be equal to -1. So what about if we have a value for R that is like sort of like this in some way? Well, what we can see from here is that there's still a linear relationship, but the values are a little bit more spread out, right? So we're going to be getting a value maybe somewhere close to like 0 point, like, I don't know. This is just a hypothetical. Like there is still a positive relationship and the value is still close to 1, but because, the dots are all over the place, we can't necessarily say there's a very, very, very strong relationship, right? And then next, say if we have, sort of the same thing here. If you guess kind of like if you drew the best fit line, right? What do you think R will be here, right? Well, R will be more closely to like, I don't know, negative. This is just hypothetically. -0.58. Let's say -0.58 because the values are all over the place. Next thing you know, say if we have values that are just plotted all over the place and it's actually really hard to draw a best fit line. Well, in this case, our R would be equal to 0, right? And a R value of 0 means no relationship, like at all. And there's one more that I actually wanted to show you. The last one. What about if I had a R? I had some data points that was literally constant. Like I had my X over here, I had my Y over here, but the Y never changed. Can you guess what an R value for this would look like? Well, an R value for this would look more so like, let's say, what do you think it would be? An R value like this, where you have X value and Y doesn't change, is also equal to 0, right? There isn't like a relationship here. So these are indicating of no relationship. I think I made these too high. Let's say this is actually negative, because the points are all over the place. I'm sorry, I think I made this too high. Let's say this is actually negative 0.1, and this would be, because this 0.64 is actually, it's not a great relationship, but it's not that far off if you round it up. And you typically don't want to round up that high though. This would be, say, like about 0.25, right? Because the dots are all over, but this is still indicating a positive relationship, and this is obviously a negative relationship, but it's not anywhere near, a perfect linear relationship.